Hello, this is Marwan Omar and my presentation today on decision trees. And I'm grateful for the opportunity to presenting at CONF-MLA, Machine Learning Automation. So here are our objectives or agenda: explaining the principles behind decision trees, describing the CART methodology, describing the building blocks of decision trees, and the key concepts such as splitting, stopping, and pruning, and then entropy and information gain. Here is an overview on decision trees. A decision tree consists of nodes and leaves, with the leaf denoting a class. Classes tall or short are the outputs of a tree. Attributes such as the gender and height are a set of features that describes the data. The input data consists of values of different attributes. Using these attribute values, decision trees generate a class as the output for each input data. Consider a classification problem that involves nominal data. Data is described by a list of attributes such as categorization or categorizing people as short or tall using features such as their gender, their height, their age, ethnicity, race, etc. as features. You call these features. How can we use such nominal data for classification? This would be a classification issue. How can we learn the categories of such data? Non-metric methods such as decision trees provide a way to deal with such data. So decision trees, in this case, they attempt to classify a pattern through a sequence of questions. For example, attributes such as gender and height can be used to classify people as short or tall. But the best threshold for height is gender dependent. So here on the right side, if we are using a decision tree for the gender could be either male or female. Within the male category, the height could be 5.6 to 5.8. If the height is less than 5.8, then the female will be considered short. Otherwise, she'll be considered tall. I'm sorry, for the male. For the female, if their height is less than 5.4, they will be considered short. Otherwise, they'll be considered tall. So a decision tree, again, another example would be for the minimum systolic blood pressure. If it's over 24-hour period, is it greater than 91? Yes or no. If it's no, then it's high risk. If it's yes, we are going to check the age. Is the age greater than or equal to 65? If it's no, then it will be low risk. If it's yes, then we ask another question. Is sinus tachycardia present? If the answer is no, then that person will be at low risk. If the answer is yes on the other side, then that patient will be at high risk. So the features here in this data, we can denote them as X1, X2, X3, X4, X5, X6, and X7. So we have the date, age, height, weight, sinus tachycardia, minimum systolic blood pressure over 24 hours, and the latest diastolic blood pressure. So we are checking each attribute. We're checking the age, which is attribute number 3, attribute number 2 denoted as X2. And then we are checking whether is sinus tachycardia present, and that would be feature number 5, X5. And then the output or the label Y would be either high risk or low risk. High risk would be, so if it's 1, that would be high risk. If it's -1, it's low risk. So we have internal nodes and the dimension index J to put a value S to X6. In this case, it's the minimum systolic blood pressure if it's greater than or equal to 91. If the answer is no, then that would be 1, which is high risk. 2 child nodes, internal or leaf, so 1, or X2, which is the age. Is the age greater than or equal to 65? Then we have leaf node as well, which is the label. So this is a classification tree. And this is the answer tx1 equals greater x6 is 115. And then if the answer is yes, 49. Then if the answer is no, then we have a label which is -1, which is a low risk. We also have regression trees. Some of the examples of regression trees are temperature, for example, and precipitation. So x1 would be the temperature, and that's a feature. X2 would be precipitation. That's a decision tree. And the labels would be kilometer and run. So here we have the features again, x2. If x2 is greater than or equal 0.3, if the answer is yes, then we have 3 as the label. If the answer is no, we are going to check another feature. Is x1 greater than or equal -5? That's the temperature. If the temperature is greater than or equal to -5, if the answer is no, then a person can run for 2 kilometers, for example. If the answer is yes, we are going to check the temperature. We are going to check the temperature in Celsius. Is it greater than or equals 33? If the answer is no, then a person can run maybe up to 5 kilometers. If the answer is yes, that means the weather maybe is not warm enough, so that person will probably run 0 kilometers. So that means that person will probably not run. So this is an example of a regression tree. Unlike a classification tree, we have different values, not just 0 or 1, yes or no. There are different values. So this is a regression tree. So the tree defines an axis align partition or the feature space. So we have x1 and x2. And we have a star here, we have a star here, and we have to check all these dimensions, whether or not the value is yes or no. So here, if x1 is greater than or equal 33, then the person might run 5 kilometers. Otherwise, the person will run 0 kilometers. So we have some familiar patterns that we can see here. We choose how to predict label given features or parameters. So the parameters are x1 and x2, which are the temperature and the precipitation. And these are called features as well. So we choose a loss between guess and the actual label. We choose parameters by trying to minimize the training loss. So in machine learning in general, we always try to minimize the training loss. The parameters here are for each internal node. We split the dimension, we split value, the child nodes, and for each leaf node, there's a label. So the parameters here don't have a fixed dimension. So we cannot apply here the gradient descent or the stochastic gradient descent algorithm. We will develop a heuristic one and build and prune. We will build a heuristic algorithm which is build and prune. So to go back to some of the previous examples regarding the classification tree here, as you can see here, we like to review some of the concepts that we covered about decision trees. So if we go back here to the initial slides, this is a classification topic. So we check the minimum systolic blood pressure over 24-hour period, whether or not it's greater than 91. And here are the features. X1, this is a feature. This is for the date. The second feature is the age. We will denote it as X2. The third feature is the height. We will denote it as X3. And the fourth feature is the weight. We will denote that as X4. Fifth feature is X5, sinus tachycardia. Sixth feature is minimum systolic blood pressure over 24 hours. And the seventh feature is the latest diastolic blood pressure. This is a classification issue, and we have only two labels, either yes or no, as the final label. So we would like to know whether or not a patient would be at high risk or low risk of having medical issue. So we check the minimum systolic blood pressure over 24-hour period, and that again will be feature number 6. The numbering of the features is important, and the ordering of the features is important. So feature number 6, we can use that to be feature number 1 or feature number 2, etc. So the ordering of the input features is not of importance. And then that's again feature number 6, and we will compare that. If it's greater than or equal 91, if the answer is yes, the next step is to ask another question, which is the age. What is the age? Is the age greater than or equal 65 years? And that's feature number 2, X2. Once we have an answer, if the answer is yes to the previous question, so if the age is greater than or equal 65, then we are going to ask another question. Is sinus tachycardia present? And that's feature number 5, sinus tachycardia. If the answer is yes, we are going to check another feature. If X5 is greater than or equal to 1. The answer is, if the answer is yes, then the patient will be at high risk. So that will be a label, and that will be number 1. So number 1 means that the patient is at high risk. -1 means that the patient is at low risk. So we have an internal node here. And we have dimensions index, denoted as J, to split value S. So dimension index J will split value S, which is X6. And then the answer for that decision tree X6, if the answer is no, the label will be 1. We have 2 child nodes, internal or leaf. So that's the leaf. Number 1 in the green box is the leaf. That's the child. X2 greater than or equal to 60. That's the leaf node. In the decision tree, we have a child node and we have a leaf node. The leaf is usually the outcome or the label. In the green box on the left side, -1 is the leaf node, and that's the label. So again, we have internal nodes and we have leaf nodes. The leaf nodes are usually the labels. So this is considered a classification problem because it classifies a patient as either being at low risk or being at high risk based on a series of questions that we have asked. So we have X1 and we have the numbers 20, 20, 11, 7. That's the feature for the date. So the date that patient walked into the emergency room, for example, or the hospital. So that's the date, and that's one of the features. That's the first feature. What was the date when a patient came to the hospital or to the ER? And then for the age is 49, so that's X2. So X2 is feature number 2. And then we have the height of the patient, 172 centimeters. So that's feature number 3 for X3. X4 is the next feature, which is the weight. The patient's weight is 70.5 kilograms. In the next question, we will answer feature number 5, X5. Is sinus tachycardia present? The answer is 0, which means no. And then the next feature is minimum systolic blood pressure over 24 hours is 115. And then X7, which is the latest diastolic blood pressure, 79. So we have Tx to the power of 1 equals X6 if greater than or equal 91. It's actually 115, so the answer is no. If the answer is yes, then we are going to check X2. Is it greater than or equal 65? No, because it's 49. So the answer is no, and that will lead us to label -1. So the label is -1 if the answer is no. And then again, we had regression trees. So some of the features for a regression problem would be X1 for the temperature in degrees Celsius, and X2 is the precipitation. So in this case, for this regression issue, you have the labels Y, KM, and run. The idea is that somebody is trying to decide whether or not they want to run. So in this case, they can build a decision tree with a regression topic. And they want to decide whether or not they are going to run based on the temperature. And they will decide how much they will run based on how warm the temperature is. So we have X1 again as the temperature, which is one feature. Feature number 2 is the precipitation, which is X2. And we have the labels KM and run. So we will do the math again. We'll compare the features with numbers. X2, which is the precipitation. Is the precipitation greater than or equal to 0.3? If the answer is yes, then that person might decide to run for 3 kilometers. So that's number 3. On the other side, if the answer is no, So if the precipitation is not greater than or equal to 0.3, then we will ask another question. We will see if the temperature was warm enough. Is x1 greater than or equal -5? So you can check for the temperature to determine how much a runner would run. If the answer is no, then that person might decide to run for 2 kilometers. So that's 2. That's a label and that's a leaf node. Again, you have child nodes and you have leaf nodes. If the answer is yes, then we'll ask another question: is x1, is the temperature greater than or equal to 33? If the answer is no, then that means most likely it was warm enough. So that person might decide to run for 5 kilometers. If the answer is yes, then that person may not run for anything. So the label is 0. That means that person will run for 0 kilometers. So they will not even run. So the tree defines and acts as a line partition of the feature space. So this is our feature space, and we split it into 2 partitions, x1 and x2, because we have 2 features. So we have feature x2 and we have feature x1. If the answer is no, then that would be our feature space. If the answer is no, we will ask another question. If x1 is greater than or equal to -5, if the answer is no, that's where the star is. That's where the feature space will be. Otherwise, the feature space will be near x1. And if the answer is yes, then you will ask another question. If x1 is greater than or equal to 33. If the answer is no, so that's where the star is, the feature space. Otherwise, if the answer is yes, then again, that person will not run for any kilometers whatsoever. So these are familiar patterns. We choose how to predict label given features and parameters. We choose a loss between the guess and the actual label. We will choose parameters by trying to minimize the training loss. And the parameter here, the parameter is here again for each internal node is split dimension, split value, and child nodes. For each leaf node, there is a label. And parameters here don't have a fixed dimension. So you can't apply DD, gradient descent, or stochastic gradient descent. We will develop a heuristic, build, and prune. And this is at the end of the presentation. Thank you.